I can actually draw a line. You could also sort it too. You have to sort it.
So like whoever's
It's exactly. Are there missing games?
Yeah, there's 20 games. And I just didn't want to give you 20 euros with data set.
Their final position is really highlighted.
I just like
So this is
Okay, so what are the designs that you came up with for this problem? Anybody want to share? Sure.
I made a bunch of columns that have the team names sorted by their rank, with lines drawn between the columns to show where the sort of team changes.
Okay, so you have like a column and then the team name, and then for every column you have the team name repeated, and then like draw lines between them. So basically like a bump chart style to show where those end up at this particular time. Cool.
You kind of have just random charts for each team, and on hoping you just highlight one team.
Yeah. Okay, yeah, so basically a line chart without the team name, you start off with something like this, and then you draw a line chart that shows the rank. Yeah.
We also explored parallel coordinates, which is along the same vein, but more discrete with the rounds.
Yes, parallel coordinates is basically a technique that we'll talk about later. And did you use like the rank as the point, as the position on the coordinate axis? Yeah. Okay. Cool. Anybody just color code the table like here?
Yeah. We did a line chart with like the rounds versus their total goals to that point, and then just color coded the point with what rank they were at.
Yeah. So why would color coding, like it works here to some degree. This is actually not color coding the rank, it's color coding like what that means for this team if they were to end like this. So the green ones are the winners, the blue ones will get to play the Champions League, the red ones will get to play the Europe League, and so on. But you could in theory color code 5 values, right? But what would be the problem if I wanted to rank code all 20 teams?
Too many colors.
Too many colors, yes. And so I couldn't really properly perceive that. Any other solutions? Yeah.
I was kind of interested in like the derivative between each round. So I was thinking of plotting the trace and then color coding the trace based off the rate change.
Okay.
I don't know.
So yeah, so like something like basically you showed the rank change mostly between, and you had a Tableau layout for that, or
Spark lines.
Spark lines. Okay, cool. So yeah, that would be another idea that you could do. Like every cell here could be a little spark line showing were to where over all the time, right? So then you would essentially have only one little, like you would have only one cell for each, like for all the rounds would be one column, and you could do a sparkline in there. So anybody thought about what this would, like why did I ask the second questions about the points?
So if you made a line chart that was just showing, cumulative points over time, the ranking at each x coordinate is the ranking.
Yes. Always, or? Well, I don't want to know, like I don't want to test you on soccer rules, but like it's also very common for teams in many sports to have the same number of points, right?
Right.
And so like that would be a little bit ambiguous here, and what happens then, there's some tie-breaking rules. It's not important what the tie-breaking rules here are, but that would be kind of like a weakness of a pure point visualization. But anybody thought about, like why do I care about points here?
You can kind of see closeness.
Exactly. So do you have like, are you in first place by a safe margin, or is it likely to change, right? So something like that, you definitely also care about. And so we'll talk about these kinds of things. So like what you guys came up with is kind of consistent with what people usually do for rankings. So there's like the two approaches that are basically like showing like the magnitude. This would be showing the points, and then sorting it. This wouldn't be very good for temporal data, but I'll show you a little bit later on how you can make this also for temporal data. And then like many of you came up with something like these bump charts here. And so there's actually a paper from Kai in 2014 that tackles exactly this problem. This is like a French soccer league, but it's the same idea. And they use the bump charts. And like I'll briefly show this video because it's kind of very illustrative for this.
At Tableau, an interactive table improving temporal navigation in soccer ranking tables. Standard ranking tables for soccer championships display teams as rows and points and other statistics as columns, such as the number of wins or the number of goals conceded. Teams are ranked according to one column, by default the accumulated number of points. In a championship, the values of the dimensions for each team change each time a team plays a game. Thus, the table contents and row ordering change for each day of the championship. Without visual help, it is almost impossible to track changes, observe teams' evolution, or generally perform temporal tasks. To perform temporal tasks, well-known visualization and interaction techniques may help, such as sliders to browse the temporal dimension, animated transitions and row highlighting to follow a team, and column sorting to rank teams according to a specific dimension. However, performing complex temporal tasks is difficult using these generic techniques. We introduced two new interactive techniques to enhance temporal navigation in ranking tables. Drag cell is a direct manipulation technique to browse time by interacting the value domain instead of the time domain. First, the user mouse clicks a cell corresponding to a team's dimension. By dragging the mouse up and down, she explores the value domain of the cell. Arrows indicate a preview of each team's behavior if the mouse were to be released, and a temporal slider displays feedback. When releasing the mouse, the table changes to the time at which the team has the selected value. The arrows disappear. For example, let's answer the following common question addressed by soccer analysts. When did a team reach the theoretical number of points, 42, to be safe from being downgraded to the minor league? Using traditional interaction techniques, the user would browse the temporal dimension to find the first time at which a particular team, here, Montpellier, obtains a value greater or equal to 42 in the points column. Using drag cell, the user interacts directly with the value domain to perform the task, making the interaction more direct and faster. The second technique, VisRank, uses line charts as a temporary overview of the championship. First, the user clicks a cell corresponding to a team and dimension. VisRank animates the table into a timeline format by widening the columns and rows. The y-axis of the chart represents the selected dimension's values, while the x-axis represents time. One line chart is displayed for each previously selected team using semantically resonant colors. An inspector shows the values of each line chart. This rank provides two scales, an absolute scale, mapping line charts on the dimension values, and a relative scale, mapping line charts on ranks. The user can also select or unselect teams to show or hide their corresponding line chart. Finally, clicking the overview chart transforms it back into a table using the inverse transition with the selected time value. To illustrate the usefulness of this rank,
Okay, so this was the technique. So I think this is kind of like a pretty nice combination of many of the things that we talked about, right? We have direct manipulation of the cells, we have like Tableau layouts, we have these bump charts, we directly switch to weights, and all of this is well thought out in terms of how to interact. So before I move on, I also wanted to show, like, who of you reads 538 occasionally? Yeah, a couple of people. 538 is this statistics website that does predictions for sports and for politics, like elections. And so here I'm showing the same data set that we just like had this exercise on, but in this case what I'm showing out here is not the actual points or the actual results, but what 538 thinks will be the end result of the league. So they essentially use kind of like these heat maps and like these redundantly encoded heat maps and numerical values to kind of give a probability of how likely it is that the particular team will win the Bundesliga. And like one thing, if you like know anything about American sports, you know that the Yankees are very dominant in baseball because they have a lot of money. This is way worse in the German soccer league. Bayern Munich wins like 8 out of 10 championships. And you can also see they give them, like in round 7, they give them a 76% chance of winning the overall championship. And the neat thing here is they have like an embedded histogram here where they show like the likelihood of them ending up in each position. And so they have 76% of finishing first, 15% chance of finishing second, 5% chance of finishing third, and so on. And all of this is very nicely synchronized and highlighted. Right? So at 538 usually has pretty cool visualizations, so I definitely would recommend to look at them. Okay, so now if we kind of ignore temporal aspects, we can go into things like Tableau Layouts. And so the classical visualization here is the table lens. The table lens, I think I showed a video before. Table lens is essentially like a spreadsheet, but instead of having all of the rows, instead of having all the cells big enough so that they can actually plot data, they show these visual marks in there. So in this case here we have bar charts, here we have categorical values, this is all the categorical values. And this is our classical cars data set where we have fuel economy, origin, cylinders, displacement, and so on. And so we can then kind of like see some of these correlations that we've seen before, that horsepower and weight seem to correlate. And then here, this is like faceted by origin. So are these European, Japanese, or Asian or American cars? And you can see that like miles per gallon, there's like a couple of gasolines or very efficient cars in here, whereas there's not so many in there. And so the table lens is kind of like a historic technique from the 90s. Ranking is, of course, like easy to do in anything like that because I could simply sort by those columns. And then we built actually a technique that is kind of inspired by it, and I want to go a little bit deeper into this. And so, like, rankings are like generally also fairly popular in many other domains, right? If you think about like what do you use rankings for in your daily lives? Like, what is the last time you looked at the ranking?
Product reviews?
Product reviews, yes. You kind of like, if you want to buy a new television, you go like you look at them ranked by like how well are they ranked on average. Other examples?
Search results?
Search results, yes. Like if you basically Google is all about ranking data, right? Other examples?
Used cars.
Used cars. In what way?
Ranking them based on like how much they cost or other issues.
Yes, that's kind of like an interesting example, right? Because used cars, you probably have a multi-objective optimization problem. Like you want to like buy something that's not that expensive, and you want to also buy something that still like has low mileage, is a good brand. So you have all of these like factors that play a role, and so like that's a good example. Like how do you pick? Can you kind of write down an algorithm that picks the best car for everyone? Not really, right? You have to always like take your personal preferences into account. Anybody looked at college rankings when they applied for college? Yeah, so that's another example. How do you rank a university? Anybody, like, do you trust those rankings? Yeah.
You rank it whichever way your university is number one.
Yes. So this is actually like it's quite interesting to say that, because when we built this ranking technique, all the university administrators always asked us, what's the ranking that our university ends up best? So, like one problem with university rankings here is that we have something like a super abstract score. Like, okay, first we have just the ranking, right? And we already talked about scoring weights versus rank. And rank is kind of like useful, but like honestly, is like the best book ever or the best university ever so much better than the second best? Like that might be debatable, right? So you might want to also, like if you're trying to quantify this, you definitely also want to look at the score. So is it better to go to MIT, Harvard, or Princeton? Like if you trust any of those like metrics, then you also definitely want to look at the score. But a score, for in the case of the university, is kind of this complex amalgamation of things like faculty, student ratio, citations per faculty, grant dollars per faculty, and reputation from employers, reputation from students. So all of this is very subjective, and we have tons of them. And so this overall score, like even like, what is more important, citations per faculty or faculty-student ratio? There's no answer to that, right? It depends on your personal preference. If you're a student and you're looking for an undergraduate college, you probably don't care so much about whether your professors are cited a lot. You probably care much more that you have somebody who can teach and who is available for you to ask them questions. And so faculty-student ratio might be more important to somebody who is picking a college as a student than to, for example, somebody who's picking a college as a faculty candidate. So what you really need to do is you need to support multiple attributes here, and you need to combine it in some way. And so like one way to combine multiple attributes is, of course, to create a weighted sum. And so you could create a score by, for three attributes A, B, C here by assigning each of those different weights. And that's what usually college rankings do. Some editor of a journal that publishes this, like Times Higher Education, says reputation is 40% of a score. But of course, this is extremely arbitrary. You could have a maximum in some cases. So if you have like three alternatives and you want to optimize one of them, you could do the product, you could have nesting, you could have kind of any mathematical function you could come up with. Could make sense in some cases. And so like what we try to do here is to make this kind of like easy for people to play around with and to kind of democratize these weighting functions for rankings. And so how does this work? So first we have these like three different scores here, and to kind of like make them, like combine these scores into, like from a Tableau layout into an overall weight, we simply transform them from individual cells to these stack types. And so this way we kind of like see, okay, the ranking is composed of those three elements, and we have a rough idea of how much each of these elements contributes. But now I could say, okay, A is not much more important to me than, let's say, B or C. And then I could correspondingly update the ranking like that. And so we've updated now the scores, but we haven't updated the ranking. And so we would have to run something like interactive transition to update this ranking here. And so you can see that kind of like Oxford, if you have A, has won out over Cambridge and Princeton. So here's like a video of, oops. Here's a video of this system that we implemented with this example of like faculty-student ratio, employer reputation, citations per faculty. We start off with a tabular representation. You can rearrange these columns. You can sort them so that you can get answers about individual of those elements. Or you can then also create these combined functions. So here, like using drag and drop, we allow people to create these combined ranking functions, in this case for a sum. and then you can click it, and you see like now we have equally rated all of those three attributes, and where do each of those colleges end up. And then if you want to change the weight here, for example, like in this case, we'll change the faculty-student ratio because as a college student that might be more interesting to me. We kind of like slowly increase that, and you see all of the animation happening, and also a little bit of like color coding here, so that if you miss the animation, that you still have a chance to look at what was going on. So that's kind of like how can I drag such that my college is like ends up best here is of course the question that every university administrator always asks. One thing that you have to think about, like this metaphor of having like long bars as high scores only works for like when we have data that is exactly like that, right? But not always is high good. So you need to kind of like have a mapping of attributes to scores. And so to do that, we kind of like devised this widget here. So we have like an input vector from like minimum and maximum. This would be like our data domain, and then we transform this into our like into the drawing coordinates. And so if we do min and max to 0 and 1, we would have a simple mapping like this here. So if we had a data point that along this orange line, we would have a bar about this weight. We could also just invert the mapping so that the low input is actually good. So that would be equally simple. Or we could do a different representation here that represents more of a mathematical function, so that y is f of x. We actually did a little study comparing those two modes, like this parallel mode for mapping and this like mathematical way of mapping, and we found that 7 out of 8 people preferred the parallel way, and the 1 person who liked this was a mathematician. How do you do this in this example here? This is arts and humanities rankings, what I'm looking at here, and you see the scores like in these distributions, and I can like dynamically drag this around, and therefore adjust my scoring. I can also switch to this function editor that kind of allows you to express like nonlinear relationships, even graphically, like here. And notice that we shade the bars. It's a little hard to see in this video if we have some weird mapping. And you can also invert scores. And so if you invert arts and humanities, Virginia Polytechnical Institute ends up on the top. Okay, like one other big thing that you want to ask is like kind of what we did with the soccer tables, right? Temporal comparisons of rankings. And like what I could do is I could do temporal comparison. How did my university progress over the years? But also I could compare multiple rankings. Like given these weightings, how is my college doing? Given these weightings, how is my college doing? And so here we kind of like use a similar idea as we like discussed earlier with the bump charts, but we integrate them with this whole interface. So we create these multiple ranking instances and then show these bump charts here on top of them. And so how does this, like in this case, we see that however it is in ranking 1, it's at position 2, in ranking 2, it's at position 4, and in the third one, it's at position 1. So how does this look like in the system? We can take a snapshot of this, and then like simply manipulate one of these columns, and then see how things are changing. And so you see the same animation, you see those bump charts kind of showing things, and if you make more radical changes, you will have some elements like down here that are going off screen. And so there we have basically just pointers down to that. So if you want to play with this, we actually built like a JavaScript version of this now. So we can go. So I'm gonna stay with the soccer theme today. So here we have soccer players, and this is like now a little bit more complex. Like this has evolved like over 5 years, but this is basically still the same technique. I have like age and height of soccer players. And like first I could sort them by, like this is a little bit more complex. I could sort them by the number of goals they scored, and Cristiano Ronaldo, and Lionel Messi, and Zlatan Ibrahimovic end up in the top 3. Not very surprising. But then I can create these combinations like we did in lineup earlier, and create the sum, like who is the oldest whole player. Doesn't make a ton of sense here, right? But I can do it. And you see that Zlatan Ibrahimovic ends up quite high up here, and like now we could ask for who are the really tall players that are also fairly old. That would be something like this. This tool, you can actually upload your own data set, and you can also embed it in other visualization techniques. So like take a look if you're interested in that. It has many other features, and I'll come back to it later. Talk about those.
What was the original program made?
This stuff was written in OpenGL, like handwritten everything. Back in 2011, when we published this, it was like there was a year after D3 was first published, and web stuff was just really starting to happen for visualization, and so this was very efficient back then. But we since ported this completely to D3. And this tool actually, like the student who implemented this, he's like a crazy hacker. He actually like made this this visualization technique is tested with up to 1 million rows, and does this very efficiently. So it has like lots of DOM caching in there and so on. It also has stuff like the table length. You can switch to an overview like this with like detail on demand. Okay. Any other questions about rankings? Yeah.
Not about rankings, but these tables in general. Some can have a lot of options you can play around with, and I can see kind of getting lost. And I'm wondering if they ever have maybe like a sum up, like metadata. This is what happened. Like it's filtered by this, it's sorted by this, it's weighted this way.
So that's a good question. Yeah. Like that's actually a topic that I'm interested in. Tracking what people have done to a visualization, tracking the whole interaction, the provenance of it. Like that's kind of, I think, a main weakness of these complex interactive systems. Like in code, you can at least see clearly what were the steps that were done, but you can't do that in visualization. There are some systems that do something like that, that have like data flow systems that are built in, but they're fairly rare. But like that's a research area that I'm personally interested in, and I'm doing some stuff on this. This gets a little bit tricky, but in detail. But essentially, yeah, that's an important problem that isn't properly tackled. Okay, so the rest of tabular data will be all about correlation, and correlation really is kind of like basically. We have these simpler tasks like exploring a magnitude, seeing a ranking, and so on. And correlation is really when I want to understand everything that's going on in my data. And so I don't really mean like statistical correlation here, but I really like this would be an example of statistical correlation, like correlating to a person coefficient. Like here we have like perfect correlation between 2 dimensions, and then we have variations thereof. And then we have examples of distributions of the data that are clearly structured, but they don't actually show a simple correlation. So that's just like another time where I want to mention that like, visualization can show you complex patterns and correlations that you can't really easily do with statistics. But when I talk about correlation for the next like part of this lecture, I really want to talk about how do 2 or more variables behave relative to each other. Right? This is the most general sense about. To think about correlation in this case. And so like super important techniques are to visualize these kinds of correlations are axis-based techniques. So we all know the familiar scatterplot, and I've shown parallel coordinates plots a couple of times already, but now we'll look at those in detail. So scatterplots. Scatterplots, they use 2 orthogonal axes to visualize 1 dimension each. So we have, in this case, we have this is a public health data set. We show like for like life expectancy at birth, and then GDP for countries. So we have like these 2 dimensions, and we see that there is a linear correlation between life expectancy and GDP. So like rich countries have populations that live longer on average. And then like you can this scatter plots are perfect for seeing like correlations between 2 dimensions. Right? If you want to see a 3rd dimension, you can plot it as, for example, the bubble size. But what's the problem with bubble size here?
A lot of overlap.
We have a lot of overlap. Yes. So we have usually whenever you talk about country data and you show population, India and China are these massive outliers because they're really big compared to everything else. And this is the same what you see here. Those 2 big bubbles are, of course, India and China. Then if I want to encode a 4th dimension, I can use color, right? But color, it kind of works here because it's not that many countries. But we have a brownish color and a reddish color, and they are transparent and they overlap each other. So this gets slightly tricky, of course, already. So how do we encode the mark is one question, and how do we deal with many points? One thing that is also useful if you show scatter plots is to use regression lines. And we also talked a little bit about regression by eye. So people are actually very good at visually fitting this regression line, even if they don't have a mathematical regression line. And this is just an XKCD comic that you shouldn't trust linear regression when it's easier to when it's harder to guess the direction of the correlation from a scatter plot and to find new constellations in it. So yeah, but usually the regression lines are quite useful and they're easy to integrate. And just remember that regression lines do not always tell you everything that you need to know, but they can be still useful. One question, what happens if you have multiple dimensions, right? And so an obvious solution is I can create a scatter plot for every combination of every dimension. And that's what the Scatterplot matrix is. So this is a matrix of size d times d, where d is the number of dimensions, and each row and column here is 1 dimension. So here I'm showing the classical iris data set that's used in machine learning introduction courses. We have sepal length, petal width, and petal length. And each cell plots a scatter plot of 2 dimensions. And so that's kind of neat, but what's the problem here?
You need a lot of charts.
I need a lot of charts. They get very small, and I'm also these charts are just inversions of themselves, right? Half of them, the half above, this chart here is exactly the same as this chart, just flipped over. So we can encode this redundant information, and in this case, also the diagonals are not particularly helpful, right? So Scatterplot matrices are definitely worthwhile if you kind want to skim your data quickly, but they have the shortcomings of not being very scalable. So we have about 20 dimensions what you can do on a computer screen. You can show about 500 to 1,000 dimensions. It's really important to also be able to brush so that you can see any correlations between the dimension pairs that you're looking at. And this is also frequently combined with a focus scatter plot. I'll show you what this means in a second. So this is when we want to blow up one of those. And if you want to kind of make this more scalable, you could cluster and aggregate records. You could help people choose dimensions, and you could optimize the ordering. So here is an example that addresses scalability. This is data board, and that shows a bin scatter plot. And I'm actually, in this case, I'm switching now to 1 million data points. And this does interactive linking and brushing for 1 million data points in the browser. And notice that they show this histogram here in the diagonal, which is actually a fairly good choice because just the scatter plot will always have just the diagonal, right? So the histogram showing the distribution of that particular variable is quite a good choice. So what they're doing here is instead of rendering individual points, they pre-process it into those bins and then have basically these heat maps here that show the density of the scatter plot instead of actually showing the scatter plot. Of course, one downside would be if I had a couple of points out here, in the corner, in a white corner of the scatter plot, those wouldn't be preserved, right? It's not, these kinds of aggregation techniques are not particularly useful to preserve outliers. And this is a famous paper from a while ago on having such a focused view and navigating in a scatterplot matrix, and I'm going to play this video.
The Scatterdice application is a prototype implementation of our Scatterplot Matrix navigation technique. Scatterdice consists of 4 main components: a scatterplot matrix, a query layer control box, and a navigation bar. The main scatterplot visualization shows the current position in the scatterplot matrix. In other words, 2 of the dimensions in the dataset. A set of simple navigation techniques allow for controlling position in the scatterplot matrix. The keyword of the navigation bar can be used for stepping one position in the matrix at a time. Movement is performed as an animated tricky transition from one scatterplot to another, where one dimension remains constant. The user can also scratch the current position in the matrix to see the animated transition from one dimension to the next. To move directly from one part of the scatterplot matrix to another, it is also possible to perform a hyperjump. If the user wants to see the intervening positions, the path planning interaction transitions automatically from one position to another. Finally, path drawing allows the user to draw the path to traverse on the surface of the scatterplot matrix. Scatterdice allows the user to build queries using the query layer box and a lasso tool, and then see how the queries distribute in other plots. The user can move an eccentric label lens on the plot to see the nominal names of the data points. This also works with query selections. Finally, the rows and columns of the matrix can be reordered, either manually using drag and drop, or automatically using the pairwise correlation of the dimensions. We will follow a use.
Okay, so what do you think about this?
These transitions are jarring.
The transitions are jarring. They can go very rapid, right? And are they helpful, do you think?
Really.
Yeah, it's like this idea of like I just have to show everything at some point and people will remember, maybe not the best idea, right? So it's kind of like this is like animation versus like showing things simultaneously. So it's not completely clear that the animation really adds a ton of value, but clearly like the one thing that I definitely like is this like explicit focus view plus this context view. And also like the whole like the brushing mechanisms and the labeling and so on. Basically, this is a very fancy implementation for looking at these kinds of correlations in high-dimensional data sets. Okay, any questions about scatter plots? Yeah.
Are we going to talk about dimensional reduction?
Yes, we'll talk about dimensional reduction in the aggregation lecture. So in that case, like here I really just talk about raw data, but like we will have another lecture on clustering and dimensional scaling and all these things. Okay, so parallel coordinates is probably like one of the like in the community, in the visualization community, super well known, but maybe not all that common. Outside of the community, like scatter plots, everybody knows them, can read them. Parallel coordinates, not so much. Parallel coordinates is like instead of having x and y orthogonal to each other and plotting it as points, I have x and y in parallel, and I represent every item as a line. So here, if I had 2 points A and B in our scatter plot, I would have 2 lines. Like I would plot the, like basically intersect the value of A with X and the value of A with Y, and simultaneously and equally for B. And then I draw like the item relationship. Like item A has a value of like a high value in X and a low value in Y. I would basically illustrate this by showing that line. And so what you can see here is this inverse correlation will result in a crossing pattern. If the values stay the same, you would have like a linear pattern on the top of it. And so here's a more complicated example. Each axis represents the dimension. The line connecting the output axis represents the records. And what's great about this is that it's suitable for all Tableau data types, including categorical data. And it also works with heterogeneous data, right? This is like basically a line chart that I've like where I've added axes so that I can plot data of different dimensions on it. And so, like we looked at this this interactive scatter plot before. Let me just see. At this interactive scatter plot before, because like what's interesting, like about parallel coordinates, it's fairly easy to see correlations between adjacent axes, but it's not that easy to see like how does fuel economy correlate with horsepower from this chart here, right? And so there's two ways that I can achieve that, either by highlighting. So here I have the high miles per gallon cars that they have low horsepower, and if I move this around, I can like interactively explore the relationship. So we can see that the the gas guzzlers have also like high horsepower. Or alternatively, and I don't think this one supports this, alternatively I could just like move, it actually does, I could just move horsepower over to fuel economy. So I can reorder my dimensions to see these relationships. And so notice that like in contrast to scatterplot matrices where I have an explicit plot of every combination, I don't have that for parallel coordinate plot, and therefore interaction here is even more important. Parallel coordinate plots have limitations with respect to scalability. Here I'm showing 500 dimensions in a parallel coordinate plot. That is not particularly useful, right? So you can't really see any data in here. This was actually the very first data visualization that I implemented. And it was slightly frustrating because there was nothing shown here. Right? This is randomly distributed data of 3 dimensions, and all you see is black. And like one simple fix is, of course, to add transparency to those lines. And if I add transparency, I can see that we have like these patterns. Like you see some of these. Well, it's random data, right? So it looks random, but you can see patterns and trends. So how can you make it scalable? By adding transparency, but of course, like what alpha value do you assign a line depends on the distribution and the scale of your data set. So that's not that easy to automatically find. You could cluster, you could bundle, or you could do sampling. Like if you have a lot of data, you could do random sampling, for example, and still see patterns quite well. So yeah, I talked about the interaction here, so I'm going to skip this one here. Another like more subtle limitation of parallel coordinates is this line ambiguity. So if we have like line A and line B, coming in from the left, we do not really know which of those two lines originated or like continuing from here are actually like what's line A and what's line B, right? This isn't obvious. And like here's a more complicated case. In this here, I don't even know anymore like which line is this here. So that's problematic, and that's particularly problematic when I have a lot of points intersecting at one particular, or a lot of lines intersecting at one particular point, as I would have if I have discrete values like integers or categories. Then this problem is especially pronounced. And so like one solution to that is like obviously brushing. I can highlight and then I can see, can disambiguate that. But also people have investigated curves to disambiguate that. So in that case here, I can see these trends clearly. So to recap, parallel coordinates are really about relationships between adjacent axes. They have like limited scalability. You can do about 50 dimensions, 1 to 5,000 records. I usually need to use transparency of lines if I have a non-trivial number of items. Interactions is way more important than for scatterplot matrices. I really need interaction to see kind of like higher dimensional correlations, brushing, filtering, axis reordering. And in terms of algorithmic support, I can use something to choose dimensions, to choose the order, like I can optimize the ordering of these parallel coordinates so that I always see an interesting pattern. And I can use clustering and aggregation of records to make it more scalable. So here's an example of where clustering is used, or well, here's an example where clustering is used to plot a very dense data set. So what they do here is that they plot, instead of showing all the data values, they simply calculate clusters with a clustering algorithm and then show the mean of that cluster. So they really show only the trends of how each cluster behaves instead of the actual data. And so here is like a more extreme case for this. This is kind of called hierarchical parallel coordinates. So what we do here is instead of showing all the data sets, we really only show the centroids plus some kind of like faded band around it to show us roughly like what's the distribution around the centroid. So here, like we're showing the cluster, not individual items, and the density of the cluster is here encoded in transparency. And you can kind of take this to the extreme. Like here we start off with like a raw data set, and then it's clustered and clustered more and clustered more and clustered more. And then we have only a single cluster left in this case. Like these charts are not particularly readable, mainly because of some of the coding choices, but fundamentally, this isn't a terrible idea. Like people have done this successfully. Who's seen these star plots before? Yeah, they tend to be very popular. They're actually pretty bad. So why are they worse than parallel coordinates? Any ideas?
It's extremely difficult to tell like how collision relates to actuator saturation or mass because they're not. You can't tell the angle between them.
Yeah, yeah. Other ideas why they're not such a good idea?
Even looking at like collision and accuracy, it's hard to tell how close those points are.
Yeah.
Yeah.
Yeah, and another thing, like imagine I had like a slope of 45 degrees. If I had it from here to here, or from here to here, that would look drastically different, right? So because I have this like triangular space where I plot this relationship, they tend to be like not particularly useful. Any like Utah beer drinkers here? Have you seen this on beer that kind of like gives you a taste profile of beers? Like how hoppy is it? How malty is it? How alcohol content? That's kind of like actually a useful example of it. This is actually not beer, but whiskey. So we have like different Scotch brands like Ardmore here, and the dimensions here are fruity, floral, body, sweetness, smoky, honey, spicy, nutty, malty. And so you get like this flavor profile. And I think that it does make sense for these, but notice that in contrast to parallel coordinates, what they're doing here is they show a separate chart for each item. So you can't really do multiple of those in a single star plot. You can do like maybe 2 or 3, but if you have something like this and you want to be playful, this isn't a terrible thing, right? But it's definitely not for visualizing high-dimensional data.
This looks like it could save a lot of space, so you can put it on the bottle. Right? With
yes.
Probably.
On a bottle, you really care about this one beer that you're drinking, right? So that's good. But if you have, like, if you want to look at all the scotches in the world, like this is actually like, there's not that many brands of scotch, but this is a long website, right? So like, how would I compare Springbank to like Lagavulin, for example? That would be tricky here, but you get this nice flavor profile, and they're visually engaging. Okay, so now to recap, more generally, like data reduction methods, which we frequently need to do, is like you can do sampling, like not showing every element, show a random subset. Like here is a paper that demonstrates the effect of random sampling on parallel coordinate plots. These are kind of like the same distributions here, but this and this isn't sampled, this here is sampled. And you can actually, there are studies that by randomly sampling a data set within certain constraints, you can still see all the trends that are relevant in the data set. And what's also important is that you, like if you like have a filter in a parallel coordinate plot that you sample, you should always only apply the sampling to the rendering, right? You should still filter out a whole data set. There are also some outlier preserving sampling approaches out there. And like the other thing to do data reduction is of course filtering. So can we define some criteria to remove data? For example, I'm only interested in data that has a little bit of variability. That's like common in genetics, right? I do like a full change and filter out all of the items that don't show any change between 2 different conditions, or consistency in replicates or anything like that. And these kinds of filterings, they can be interactive and they can be combined with sampling. Okay, now it gets like hybrid into hybrids. We'll talk about how can we, like basically these access-based techniques that can actually combine them in interesting ways. And so this here is a technique that's called FLINA, Flexible Linked Axes. This is by Jörg van Wijk, one of his students. And that's kind of like basically you can choose to combine two axes, and then you can either just like project the points between them, or you can connect them with lines. And so just with this basic idea, I have those two options. They show that they can actually recreate all of these different visualization techniques. And so here's an implementation on the web of this by somebody else. Okay. Let's see. I have my, like here I have miles per gallon, and you see, oops, oh, it's always a little. Then cylinders, and now I can show like a parallel correspondence between those two. And then I could manipulate those, and then either try to make them parallel really. And now I could add like displacement here. In this case, I'm going to make this a scatter plot. And I could manipulate like the positioning here as well. Not something that I would recommend, but it's possible, right? And by using this, I can like basically recreate all of these kind of like complex axis-based visualizations by myself. Another idea, like basically these like what you see here are, it's called connected charts, and this is like if I have charts that are related, like in this case here we have different performance indicators for like a computer. You could use something like parallel coordinates to show these connection lines to show the same items, right? So you see that they did this here with like various line charts and time points and scatter plots, and so therefore kind of like you get something like parallel coordinates here on this side, and this like looks like this is basically well, you have a like more linear trend here. So like these kind of connections are useful if you want to explicitly show relationships between multiple charts, but of course they tend to get fairly cluttered. And I did show this before. This is like one of our techniques where we combine, like where we use these kinds of axes to combine this, like show connections between heat maps and some numerical variables, and then combine this with a scatter plot, and then here with like a like basically some categorical visualization, and then some heat maps again, and so on. Okay, so now I want to move on to any other questions about these axis-based techniques? Great, so like one special case is categorical data. Like categorical data did kind of work in scatterplots, but if you like show just categorical data next to each other, they don't actually work that well. It works well if I have a numerical, categorical, numerical, but just like looking at relationships between categorical dimensions is fairly tricky, and that's where parallel sets can actually help. So they build on the idea of parallel sets to handle categorical data. They're discrete, like categorical data where we have that is discrete, we have a small number of values, and we have no implied ordering between attributes. And so what we want to do is find these relationships or correlations between attributes. And so this is kind of like what the idea is here. Like remember, this is the Titanic data set between like where we have attributes such as like passenger class, gender, and whether they survived or not. And so here the idea is to simply have like an axis like in parallel coordinates, but a data like an item like a value is now not a point, but it's a bar, and the bar is as big as how frequently this occurs in the data set. So basically this shows us here we have like not a lot of second class passengers, a little bit more first class passengers, but the most third class passengers, and actually like a fairly sizable amount of crew here. And then we do this for each dimension. Like here we have class, and then down here we have sex. And then we see the relationships. They are shown by these ribbons between first, like you see that essentially first class splits almost evenly between female and male. Third class is predominantly male, and crew is like with a like significant majority male, and there's only this one outlier here, or this thin outlier here that is female. So this is a paper from 2005. Here's an implementation in D3 with the same data set here. And so you see like survived, perished, sex, age, class. And so if you like hover or survived, you see that there's like roughly an equal split between sex, female, and male. But if you hover or perished, you see that like if you died, it was more likely that you were a man than you were a woman. So if I looked at females, like this is the group of females that have perished. And as we also seen before, first class here is there's a lot of people in first class that survived, and only like this smaller arrow here shows us people in first class that actually perished. So all of these things matters in the Titanic disaster. And I can like rearrange things here. The direction is a little weird. So I can sort it by size or like values and so on. You kind of like you can take this to the max, and it gets kind of fairly cluttered if you have a lot of categories, right? So here we have 3 dimensions and like many categories, and then we get into these like parallel coordinates like thing where we have a lot of clutter in here. What they also do here is they show like a histogram for each of those dimensions. That's also something that they can do on top of parallel coordinate plots if you want to. And then they also discussed a couple of interaction techniques so that you could reorder them to reduce the crossings and so on, or you could aggregate them dynamically to summarize second and third class here into one big second and third block. Or you could filter it by simply dragging it off the screen, and then you only look at first and second class anymore, and not at third. Highlighting equally, so all of the like interactions that you can think of. Okay, so these parallel sets are like a pretty good visualization technique for categorical data, but you can also visualize categorical data in like tabular grid or matrix-based representations. And so tabular representations are basically what we had in the exercise with the color coding here. We've seen many of them. We've seen them in ranking, but now let's look at them more generally. Like in the tabular representation, it's like a spreadsheet. Each variable is its own column. Each item is a row, and each cell is the value of like the combination of item and dimension. And then I can use visual encodings to make it scalable. Like here is one example where we have like a couple of different visual encodings. Like here's categorical data at the top, and then we have like bar charts here, and then we have like divergent bar charts at the bottom, and then we can also kind of like aggregate here. Like this is about like this column here represents about the same number of items as this one here, but instead of showing individual items, we are actually showing distributions here. Here's a different way of showing these distributions with these box plots. And then, like I showed this before. I don't know why this is happening. Okay. I showed this before. This is like this idea of the table lens and of Taggle. And here I'm encoding categorical data. Now I'm going to switch to this AIDS data set. I'm encoding categorical data like with labels and color, but I can also switch the visual encoding here. So I could say choose like a matrix representation. And so now here I kind of like have color still, but I also have positional encoding of categorical variables. Or I could do like just a string, that would be an option, or I could do this kind of like different like non-colored representation, or I could do just the color and the label. But like for numeric data now, I can like do this with like sorting, or I could also, in this case, I can also group. So here, I've now grouped by a categorical variable, in this case here by continent. So you see like Africa, Asia, Europe, and I actually have summarized countries in this group, and I could even collapse them in the Tableau layout like this to, like in this case, I'm only looking at the relationships of the continents and get like super aggregate representations of this data set. So now I have only the continents and get like basically summary statistics about like how many people know that they have AIDS or HIV in this case. What is the distribution of the urban population in these countries, and so on. And I could reveal this on demand if I wanted to. A different technique that is more meant for presentation is Vertifier. And Vertifier is like really like all about how can I specify like a tabular representation like this to how can I interactively design this. So let me show the video.
With icons. When she moves her mouse on top of any tool icon, a tooltip appears at the top of the page to recall its function. Tools are organized in groups. Clara first expands the MISC group and clicks on the H icon adjacent to the first row to mark it as a header row. She does the same for the left column. Then she expands the Shapes group in order to turn numeric values into shapes. She clicks on the circle icon next to the first row of the table in order to turn its values into black circles and squares. She is satisfied, so she presses the same icon on the next row and drags down until the last row. This instantly turns all table cells into circles and squares. Now Clara wants a more compact table. Each row can be resized independently using the slider placed next to it. Moving the slider to the right increases row height, while moving it to the left decreases it. She sets all rows to their medium size by pressing on the topmost slider, drags down until the last row, then drags left to modify all selected sliders. She does the same for columns. She also zooms in using the provided functionality of the browser. Now she wants to tidy up the table. She drags over all black arrow icons, which immediately rearranges columns by visual similarity, which moves similar countries next to each other. She does the same for rows. Now indicators that are similar are close to each other. To better see similarities, she removes the grid by setting all white separators and black separators to their minimum value. Clara continues to format the table to exhibit more patterns and convey a clearer message. This includes inverting the values of a row, importance of a good pay, to better show its correlation with another one, the household income. She also emphasizes two rows of a specific type by changing their visual encoding, increasing their height, and dragging them aside. She encodes women's suffrage year using lines, and household income using a bar chart. She can choose to reorder only a subset of the rows or to reorder all rows. Now she can already see country groups with Czech Republic in between that she moves away. Finally, Clara adds separators, annotations, or emphasized groups.
So I think this is like how I would love to work with Excel, right? With these kinds of interactions, these cross-filter interactions. Like this is really what is most impressive about this particular technique. And you can actually play with it, like just load your own data from a Google spreadsheet and then play with this technique. So I really love the interaction here. Okay, the most scalable tabular data visualizations are these dense pixel displays that we usually call heat maps. So here, each cell is a pixel, and the value of this is encoded in color or value. And so that obviously only works for data, like if we have multiple dimensions, data that is of the same scale, right? Like if I have whatever age and like 100 meter runtimes, I can't really do that efficiently. But if I have data of exactly the same scale, then I can use these heat maps very effectively. The one thing though is that order is really critical for interpretation. So here, like we have an example on the left that is unordered, and you can't really see any patterns, right? Like, or can anybody spot patterns? Like there's like, you can say something about individual columns, but you can't really say anything about the overall heat map. But if you find a good ordering, a good seriation, you can actually identify, like, here's a red cluster, here's a red cluster, here's a blue cluster, here's a blue cluster. And that's basically, you need like good algorithms to do that, good seriation algorithms to do that. So either you have an ordering inherent here, or you need to use something like some seriation algorithm to really like reveal those. And they're super scalable. Like, I can actually get away with a single pixel per item. And even if I have more items than I have pixels, if I use a good clustering algorithm, I can still get like this natural aggregation here. And so here would be a comparison of like a heat map and the parallel coordinates plot. The same data set, you see that this is a much more compact here, and that maybe I can see the trend a little bit better in the parallel coordinates plot, but I can also easily see it in the heat map. So like more compact, maybe a little bit harder to spot individual patterns. This is just to recap, like 3D. Like, anybody can spot a pattern here? Nobody can spot a pattern. If I plotted this as a heat map, we see this question mark pop up. Right? So heat maps are pretty good. This is an example where a heat map was used for heterogeneous data. This is from a famous neuroscience paper, neurogenetics paper about brain cancers. And we have these 4 different tumor types here, 1, 2, 3, 4. But then we have different data types: mutation, gene expression, copy number, and mutation status for each of these genes, and they all use the same color scale, right? So that's like not really a well-designed chart, because like there's a lot of redundant data, and we really shouldn't interpret any patterns in this. We can read individual items, and we can kind of judge consistency for each row, but we shouldn't judge anything globally here. Just recall that we have problems with red-green color maps, and that we have problems about relative like effects of neighboring darkness items. Like this is again red-green, but here we have this effect of like these two are actually the same value. So that these are some of the things that you like have to deal with when you have matrices like this. But this is the same. Like I showed this extremely cluttered parallel coordinates plot earlier. This is a 500 by 500 matrix, and you can actually see some patterns, right? You can see structure. So it does work just fine. Like compared to the parallel coordinates plots, clearly much better. So yeah, the last minute, I just want to wrap up by like space filling approaches. But now we've talked about heat maps, but heat maps always have like or tabular approaches. They have always a consistent row and a consistent column, and so they're easy to kind of read like that. But there are also approaches that are space filling in another way. Like the useful one is clearly the heat map, the tree map. So here we have like some kind of partitioning algorithm or some partitioning variable actually that we use to split up this data set, and we can see each of these unique clocks here represents something. But there have also been other ideas, like basically just to use these pixel-based displays and to be more creative about how to arrange them. And so, like, I'll just show this example here. I would have like a 6-dimensional data set, and I represent every item as this like 2x3 square, and color code them, and then arrange them either circularly or according to some pattern, or using a Hilbert curve so that we have all the things close by to each other, and then you create these very dense pixel displays. And so this was like a popular technique back in the 90s, and then you get stuff like this, but that, like, I have never really learned how to read them. And so they might have, like, especially combined with a Hilbert curve, that could be something smart, but it's kind of like tricky to really understand charts like this. So that wraps up Tableau data. We'll not be here next week, and then we'll continue Tuesday, a week from now. Thanks.